as you heard, I have a few things that I could talk to you about, but I'll talk to you about my intense laser work, since that is a little bit different. And do we have a pointer? Oh, we'll see if it works now. Okay. So, I don't need to repeat the introduction, but I thought I would say a little bit more about what Seth alluded to, is that I have worked on a number of things during my career so far. The two areas, broadly speaking, are ultra-fast and ultra-cold. We've heard quite a bit about ultra-cold. We haven't heard so much about the few body aspects of it that I worked on, starting during my time at ITAMP and after until now. But most of my work on ultra-cold has been on that few body side. I've also done quite a bit of ultra-fast work on the ultra-fast side, and that's partly a function of where I am. At Kansas State, we have a large lab. I don't know, eight AMO people, I think, 8 or 10, all working generally in this area of ultra-fast physics, ultra-short pulses, intense lasers, that sort of thing. And so I have experimentalists down the hall who are doing cutting-edge things, and so it's nice to take advantage of that. So I've been doing a fair amount of that. These seem to be quite orthogonal areas, and in fact, really they are. And it's a little bit difficult to keep up on both, since they're both rather hot topics fields. But, you know, somewhere in the middle here is a methodology. Mostly what I'm doing on the ultra-fast side is also few body systems. And so my methodology, the way I tackle it, is partly what unites my two programs, my two research programs. Now, maybe this is a good point to mention a couple historical things, since this is a reunion, this is a sort of a symposium looking back at 25 years. Most of you probably don't know, but when I graduated, I had both an NRC postdoc offer and an ITAMP postdoc offer. You know what I chose. And at the time, I had actually many people asking me why in the world did I choose to go to ITAMP? Because at the time, for one thing, the pay of an NRC postdoc was much, much larger than the ITAMP postdoc. And it still is, okay? And so I had people asking me. I said it just offers many more opportunities as far as I was concerned for my professional career. In particular, the one thing that I really valued was that it gave me a chance to do what I wanted, right? It was an independent position. I didn't have to go do what somebody else told me. And that was something I really valued because, in fact, I had a lot of ideas I wanted to work on. And one of the consequences of that was I didn't actually end up collaborating with so many folks here, certainly not as many as many of the rest of you have. But nevertheless, it was a valuable experience for me, simply because I could do that. Now, one thing that I will mention that, again, maybe I don't think a lot of people realize, is that one of the things that has gotten a lot of attention in my body of work on this ultra-cold side is three-body recombination, sort of our first FMO paper. That was published when I was at ITAMP. That wasn't published when I was a student. I did that afterwards. So that opportunity to work on the things that I wanted actually gave me that start, basically. But today, I want to focus on the ultra-fast side. And one thing I will mention, and Seth's picture illustrated that nicely, ultra-fast is a really moving target. Okay, he showed pulse lengths that changed by 7 orders of magnitude over the last 20 or 30 years. And the whole time it's been called ultra-fast. So ultra-fast just means whatever the fastest thing available is. It's not a particular definition, right? And ultra-cold, it's not such a moving target, right? You get below microkelvin and that's basically ultra-cold. In ultra-fast, it's a little bit different. One thing, maybe one more historical point I'll make, is that probably all of you know Peter Zoller. Many of you know Keith Burnett, right? Both, of course, have done a lot of ultra-cold work. Both have ties to ITAMP. Both did strong field physics before they did ultra-cold physics. Okay? That was in the late 80s, early 90s. In hyperspherical coordinates, in fact, yes. Peter has done hyperspherical, which I won't talk about. So anyway, before I go on, though, I thought I would just acknowledge the folks who've done most of the work in my group, and then close collaboration with an experimental group there at K-State of Itzig-Benitzak. And again, since we haven't really heard anything about intense laser physics, and since it's fairly unfamiliar, I think, to a lot of you, I thought I would start maybe back a few steps and just give you a sense of what intense laser physics, strong field physics is about. So if you think about intense light, probably the one thing you might think about is, this kind of a thing, right? The light at the surface of the star. It turns out, if you sort of average overall wavelengths, this is a very rough number, but you get an intensity of 6 times 10 to the third watts per square centimeter. The fields I'm talking about are only about 10 orders of magnitude larger, at 10 to the 13 to 10 to the 15 watts per square centimeter. And by the way, this is nowhere near the peak intensity that people can get. That's just what I'm talking about. I think the record peak intensity is around 10 to the 21, 10 to the 22 watts per square centimeter, at which point you have to start worrying about relativistic effects, pair production, and other kinds of things because the field is just simply so strong. Okay? We won't be in that regime, but we'll still be strong nonlinear effects. Okay? And to put that in perspective, we're atomic physicists, so let's talk about atomic units. 1 atomic unit of field corresponds to an intensity of about 3 times 10 to the 16 watts per square centimeter. Now, these electric fields seem weak compared to that, except it only takes about 6.25% of this intensity to field ionize the ground state of hydrogen. Okay? To go out over the barrier in the picture that Seth showed. So in fact, these intensities are plenty to just completely ionize hydrogen. Okay? And of course, this number is based just on the field that the electron sees in the Bohr 1s orbit. So the other side of this is what is ultra short. Okay? So what I'm going to be talking about typically are sub 10 femtosecond pulses. Okay? So the picture of the pulse lengths that Seth showed that he borrowed from the Corkum paper, we're a little optimistic. Okay? We really haven't had 10 femtosecond pulses since the mid-80s. That's mostly only been the last 10 years or so, 10 or 15 years. These days, 5 to 6 femtoseconds, even 4 femtoseconds, are fairly routine to generate, and those are 1.5 cycles, 2 cycles, 3 cycles sort of laser pulses.
Can I ask you a question?
Absolutely.
So it only takes 1 volt per centimeter to field ionized hydrogen if you're willing to wait long enough.
Of course.
So what do you mean by the state?
Over barrier.
Oh, it's classical.
Classical over barrier, that's what I mean here. Sorry, that's a good clarification. Because absolutely, any epsilon of field is enough to field ionize it if you're willing to wait long enough. But this is over barrier ionization of the ground state. So that means you bend the potential so far over it classically leaves. So that's a strong field. So in other words, these fields are comparable to what the electron sees from the nucleus. Okay?
Ionization potential, important. Ionization
Yeah.
potential. It's barrier ionization potential.
That's right. You lower it to the ground state, exactly. So to put these sort of sub 10 femtosecond pulses in perspective, some of the shortest vibrational periods, nuclear vibrational periods in molecules are around 10 femtoseconds. Those are for light atoms like hydrogen. Okay? So we're at a time scale to resolve those things. Electronic motion, okay, is on the order of 150 attoseconds. That's the period of a 1s Bohr orbit. Okay? About 150 attoseconds. And again, as the pulse length picture that Seth showed, the current record for pulse length is 67 attoseconds. Okay? 67 attoseconds. Now, to get such a short pulse, you necessarily have to have a large central frequency, and those are typically going to be tens of eV, 90 eV, something like that. So you have 67 attoseconds, but it's a 90 eV photon. Okay? Yeah? Because, yeah, this is in fact a common mistake. The period for 1s electron to go around is not 1 atomic unit. right? It's 2 pi times that, because the 1 atomic unit of time times 1 atomic unit of velocity is, I mean, that gets you 1 atomic unit of distance, so it's not far enough. It's not the whole cycle. Okay? So again, that gives you a sense of where we are. So most of what I'm going to be talking about is more in the sub-10 femtosecond region rather than the attosecond region, because currently attosecond pulses are still linear processes. They aren't intense enough to do multi-photon processes for the most part. That's not uniformly true, but that's mostly true. And what I want to talk about is really nonlinear things with this, multi-photon physics. And so I'm going to talk about a little bit longer pulses where we can drive high-order things. So again, just to get you oriented to the kinds of things that these laser pulses make possible, I like to flame things a little bit, inflame things a little bit with statements like that. Einstein was wrong. Okay, so what do I mean? Typically when we teach the photoelectric effect, okay, we say we have some material, we shine light on it, and an electron comes off if the photon energy is bigger than the work function, right? And the energy of the electron is just the energy of the photon minus the work function. And we say that the energy does not depend on the intensity of the light, right? How many photons depends on the intensity, but not the energy. We say that there's a minimum frequency to have the photoelectric effect. But in fact, if you take an atom and you shine an intense laser on it with intensities around 10 to the 14 watts per square centimeter, then you can measure a photoelectron spectrum like this. So just focus on the top one here. Okay? So this is photoelectron spectrum that counts as a function of photoelectron energy. And of course, notice that this energy, by the way, this is with 800 nanometer light, so the photons are about 1.5 eV. But notice we have or electron energies all the way out past 40 eV. Yeah.
In Einstein time, they use the candle, not laser.
That doesn't change my statement, does it?
I think it's changed intensity, that intensity matter, I think.
Just because he didn't have it available, you're saying Einstein couldn't imagine things that weren't available?
I make up my statement.
Okay. So you have, with this intense laser, you have a photoelectron spectrum. Notice these peaks. Those peaks are separated by 1 photon. Okay, so you absorb the minimum number that you need to ionize, which is not 1 at this photon energy, and then you absorb more. Okay, so each of these are multi-photon effects, so you can absorb many more photons than are necessary to ionize. Okay, this is called above threshold ionization. It's actually a terrible name, but that's what's stuck. Okay, and this isn't an especially impressive example. There's measurements where they see out to order of 100 or more extra.
But the API also refers for bulk? No.
Yes, yeah, you can see it on the bulk too.
Bulk as well?
Yeah,
Because I thought that coolant needs a separate coolant.
no. No, this, as you'll see, this is simply energy conservation. To see ATI is simply energy conservation. You don't need a coolant potential.
Well, but free, sorry. Why Wesley? Let Wesley have.
Yes, Vasily.
It's interesting because important, as you mentioned,
Yeah.
the population of photons here, because photon wave function, the question, how many photons in this laser beam between?
It's completely classical. There's gazillions of photons.
I mean, it's not, for example, as a usual my thermal light or something.
No. This is,
Close.
no. People don't even talk in terms of photons when they're talking about the laser in this case, in terms of how many photons there are. It's completely classical. Okay.
Yeah, what I was going to say,
Yeah.
if I have a free electron, it cannot absorb photons because it cannot satisfy both momentum and energy conservation simultaneously.
That's true, but as Seth told you about the 3-step model, this electron goes out and comes back.
Yeah, so
When it comes back,
coolant, yes.
no, it doesn't. Absolutely not. In fact, the model that he said ignores the Coulomb entirely. So it
Then
doesn't.
you have to have acceleration.
That's what the field's there for, right? There's an external field, right? The external field's oscillating back and forth, so it gets driven out on one part of the cycle and driven back on the other part. So that's all completely classical, no Coulomb required. In fact,
You don't have a photon absorption. In this case, this conservation doesn't work.
Yeah.
You have many photons. You
Sure.
know how many.
Sure. And you don't know, these aren't one at a time necessarily, right? It's not like it absorbs one more and one more and one more, right? It can absorb many at once. We don't know. It's a multi-photon. It's really nonlinear.
Einstein was wrong.
So the energies of these photon peaks are simply still energy conservation. It's NH bar omega minus the work function. That picks all of these out. But it does depend on the intensity of the light. And there is not a minimum omega because I can absorb lots of photons to get out in the first place. Okay?
I bet if you asked Einstein, he knew about strong fields, right?
He probably would imagine it, yes.
I mean, he knew he wasn't in the classical limit.
Right, right. Yeah.
And by the way, I always thought it was very funny that chapter 1, they use the photoelectric effect to prove that the photons exist.
Right.
Chapter 21
Is calculated
is the
without,
photoelectric effect by perturbation theory
with classical light.
with classical light.
Absolutely. And that's
How do we change it? How do we
Same
change
book.
it?
Every book.
because you don't need a particle to get this picture, because you can calculate this picture with purely classical light. There's nothing about particles in this picture.
No, but there is some contradiction, which I return to what Lee asked. Yeah. If you seriously have a fixed number of photons, n,
Yeah,
you have a momentum energy conservation. If you don't have if you have a classical light, your n is a not good quantum number. Yeah.
right.
I would like to understand this. For example, very age of a U curve, absolute age. Yeah.
Yeah,
When you have all energy from you being absorbed by one electron,
yeah.
is it correspond energy momentum conservation or not? If it correspond, I will put light dispersion relation and I will see that it doesn't work because conservation works. I talk about this high energy,
Over here?
even down, until
Oh,
all
maybe this part?
Down. Until
Oh.
all energy will not absorb, all energy of beam.
Oh yeah, no. I mean, only a tiny fraction of the beam is absorbed, for sure. Right? Because, I mean, again, the beam has gazillions of photons. This is 50, 70, 80, 100. That's negligible compared to the number of photons in the beam. Now, for the most part, I mean, energy is conserved. That's what this expression is, and that's how we pick out the peaks.
Because you assign this for photons, one photon.
Yeah.
Yeah, this conserved.
That's right.
In classical light, you don't have a number of photons. It doesn't-
No, that's right. But this is,
picture
it's just
shows-
harmonic. It's harmonic analysis. I mean, you have a periodic signal, and so energy conservation comes out of a time integral and perturbation theory, right? That's all it is.
Well, I don't understand the objection.
No, my objection was that if this peaks here we count as a one photon absorption, two
Yeah.
photon absorption,
Yeah.
something, I will follow the curve. I will follow the curve up to a logical end of this curve. It should be ended. Yeah, this curve of energy should be ended somewhere. Yeah.
Sure, but n is 10 to the 8. N is 10 to the 8. Okay? The number of photons is 10 to the 8. So yeah, you could follow this all the way out to 10 to the 8 if you
I
want.
know the number of photons in classical light. This is my absorption. I
Yeah.
don't understand.
But that's so far from where we are that it's not an issue. That's what I'm saying. Yeah. But anyway, this is exactly the point. I mean, very nonlinear effects in the sense that many photons can be absorbed. Okay? Now, this is just energy conservation, and so we can see it when more than one particle absorbs the photons. Okay? So we just take, for instance, H2 plus, absorb lots of photons to ionize it, that produces 3 particles. Those 3 particles share that energy, right? But it still has to be quantized in terms of the number of photons. And by the way, maybe I should have started by saying, when I say photons, I just mean h bar omega of energy. There are absolutely no literal photons in what I'm talking about because it's a purely classical field. So photons just means h bar omega of energy, and it's a lot easier to say photons than h bar omega of energy. Okay? And so that's what I mean here. The initial
Even though
energy.
H bar is in that expression.
Yeah.
Actually, it's not really there. It's just that you still get those peaks classically.
Yes. Yeah.
Because the oscillator that's quantized has frequency omega.
That's right. That's right.
But peaks, energy peaks was h bar omega.
In such a picture, exactly. Now in this picture, where I'm showing electron energy and nuclear energy, this energy sharing shows up as diagonal lines. So lines of constant energy, right, which you can see, are exactly these multiple degrees of freedom, these multiple continua sharing that energy. And what's interesting here is we have a line of constant energy for absorbing a certain number of photons. The interesting thing here is this tells us how the electrons in the nuclei share that energy. Okay? Now, this was a calculation we did, and you can see this actually isn't that old. Okay? So people hadn't, even though they'd been doing these multiphoton effects for a couple decades, they hadn't really thought about what happens so much when you have multiple particles, especially in a molecule. Okay? And shortly after we published this, Reinhard Dörner's group went and measured it. So they did, instead of H2+, they did H2 with multiple photons breaking into a hydrogen, neutral hydrogen, a proton, and electron, joint energy spectrum, and they see exactly these multiphoton peaks. But they have to be there, because this is simply energy conservation. Right? Very simple idea. So it applies to any system, in fact. Okay? Any number of degrees of freedom. You just have to plot it, including all those degrees of freedom, and you'll see exactly this. So no matter how much energy you pump in there, it can only be shared among the degrees of freedom possible. Okay? Now, one of the goals of ultra-fast, strong field physics is coherent control. Okay? Controlling in much the same way as many of you have talked about, in controlling the outcome of some process. Now, typically, this is a strong overlap with the chemistry community, so the control that they want to exercise is control over, say, a chemical reaction. Okay? And the way that this will work quantum mechanically is essentially Young's double slit. Okay? I don't have to explain that to this crowd, but you just have two pathways and they interfere. So and of course the interference is controlled by a phase difference. In a quantum system, again, I don't have to explain this in detail, but if it's a two-level system, you have two pathways. Now, the difference is that if we have a strong field, I can get to that upper state with one photon and maybe three photons. Okay? And this was, in fact, the Brumer-Shapiro scheme that I think Roman mentioned yesterday. This is one of the canonical coherent control schemes, as you interfere two different pathways. They were thinking one frequency and a different frequency, not short pulses, but in a short pulse, you might be able to do both of those paths simultaneously just because it has a broad bandwidth. Now, if you're going to a continuum, things change a little bit. You start from an initial discrete state, say a vibrational state of H2+, and you go to a continuum state. Okay? You can do that with one photon, or you can do that with two photons. And of course, what you're going to see in terms of the spectrum of the particles coming out is an interference pattern, which is just Young's double slit, and it's controlled by the phase difference between those. Okay? But the double slit will appear as a function of the kinetic energy of the fragments. Okay? So, one way that people have been trying to exercise this coherent control in recent years is taking advantage of the fact that they do have short pulses. They do have these few cycle pulses. Okay? And here I've plotted the electric field in envelope for a 5 femtosecond pulse, which at 800 nanometers is about 2 cycles, okay, and a 10 femtosecond pulse. And you can see that in the classical I want to say classical, in the picture, the 3-step model, which is what people consider canonical in strong field, that's the way everything works, okay? Everything depends on the field. And so the peak value of the field is what's important. And you can see that for the short pulse, the peak value of the field depends strongly on this carrier envelope phase. Okay? And the longer pulse, if I go from the peak to the next one, the peak value just isn't that different. So we don't expect much dependence on the CE phase. Okay? And again, the picture being that it's all controlled by the field. So since we discussed yesterday about theory leading and experiment following, I thought I would show this example, because in 2004, we did a calculation for H2+ dissociation as a function of this carrier envelope phase. And you can see we can control the direction that the proton goes. Okay? So as a function of the carrier envelope phase, we can control which direction the proton goes. Okay? In HD+, where the two nuclei are distinguishable, we can control the channel. So we can control the yield. Okay? Those are chemically distinguishable outcomes. So with the CE phase, you have some fidelity in controlling how that reaction happens. Now, you'll notice we did manage to get a PRL out of this because it was a hot topic. Yeah, Vasily?
Rotational, vibrational motion of H2 plus, are they spoiled, controlled, or it's not important for you?
I'll get to that. I'll get to that. Roman?
So that's the direction?
I'll get to that too.
Okay.
Okay? But the key point, and again, this was with Rick's point, we got a PRL out of it. Here was the first experimental observation. You notice that's in a little different place, right? And they didn't come to us and ask us to do theory for it. So, but they did see it, so that's good news. They saw it on a little bit different system, but still, as a function of the CE phase, they saw exactly this kind of control that we were talking about in the direction of the, in this case, deuteron. Okay?
Yeah, may I ask, this experiment is a single shot or they have to repeat?
Oh, this? Oh, no. This is millions of shots. Absolutely. No, there's, you know, they do one shot and they get 1 point. Okay? So, then, of course, we came along a little bit later and showed how you can enhance this effect. You'll notice the asymmetry here, which is defined as the difference of a deuteron going this way and this way divided by the sum, so it's a normalized asymmetry, ranges from minus 0.2 to 0.2. The maximum it can go is minus 1 to 1. That's the point of, one of the points of plotting this. So they saw some control. We showed a little bit after this, this experiment how to enhance that control by quite a bit. Okay? And then somewhat later, actually just last summer, the experiment was done directly on H2+. And one of the reasons to do it on H2+ rather than H2 is that in H2+, we can do a complete calculation. Okay? Except for ionization, because we can't do that complete a calculation yet. Okay? So as long as the intensities are low enough and that ionization isn't so big, we can do that calculation. And this, in fact, is the calculation that goes with it. So you can see one of the issues here is statistics. Okay? Although you can see sort of these stripes like we see in the theory, there's some statistics issues still to be improved upon. Yes?
How do you enhance the asymmetry? Is there a short answer to this?
There will be a short answer after I explain the asymmetry. Okay? So, and this is what I wanted to get to. So one of the discussions that also came up yesterday, especially as a potential bridge between, you know, ultra cold stuff and things that are going on and ultra fast, is that we want to treat complex systems. We want to treat correlated motion of complex systems. One way to do that is to just directly try to calculate these things, right? The problem is, as you get more bodies, more degrees of freedom, the computational complexity grows exponentially. You quickly run out of enough computer power. Jack can't even provide us enough computer power to do these kinds of things.
It'd be nice to try, though.
So, the other way to go about it is to try to gain a deeper understanding of where these come from that apply to all systems, general principles, right? Symmetries, if such things are available, okay? And in these strong fields, symmetries aren't obvious, but one thing that we did find is that all of these CE phase effects turn out that you can think of them as interference of different n photon amplitudes, okay? And that's what I want to explain quickly here, because that will answer many of the questions. And to give you an idea of how simple it is, and the simplicity leads to the generality, is let's consider the Schrodinger equation we want to solve. Okay? It's a time-dependent Schrodinger equation because this is a non-perturbative field. This field is really strong. This is a dipole interaction, and this is the carrier wave and the CE phase here. This is the field-free Hamiltonian. This doesn't specify what system I'm talking about. It could be this chair. Okay? That's completely general. But you'll notice that the Hamiltonian is periodic in this parameter. Okay? So the solution is periodic in the parameter, so we can write the solution as a Fourier series, right? And that's an exact expression. And that's really the whole story, because once you write this down, you can see that these amplitudes are independent of the CE phase. So we're able to write in the solution the CE phase dependence analytically. Okay? It applies to any system. And once you have a wave function, of course, we can write down any observable. Okay? We'll just write it down in a general way. So, for instance, if you want the momentum distribution, you take your wave function, you project it onto scattering states, incoming spherical waves, outgoing plane wave with momentum k. But I already wrote down the expression for the wave function, so we can substitute it in there, and you get an expression like that. Okay? Completely general.
The solution for kick rotor, yeah?
It could apply to that as well, right? But this is not explicitly tied to any particular Hamiltonian. Okay? All the CE phase is right here. These amplitudes are independent of CE phase. And you can see that you can get all the interpretation you need from this. Okay? So, in particular, to get a CE phase effect, you need these two amplitudes to be non-zero in order to get that contribution. So these are labeled by different n's, which will turn out, and I won't show that because I won't have time, those turn out to be the photon numbers. Okay? We can show this in a not exactly rigorous, but a fairly suggestive way that you can interpret the n's as the number of photons, the net number of photons absorbed. Okay? So these two amplitudes have to contribute at the same momentum, which means that you have to have different numbers of photons contributing to see CE phase effects.
So this is sort of similar to this.
No, absolutely not. Actually, I won't say it that strongly. It's similar, but it's not Floquet. It makes no assumptions.
Similar because there's no teeth.
It's also a photon number, but that's where the similarity ends. Okay? Floquet theory says, oh, look, it's periodic in time, so I can write the solution as a periodic function with a time exponential there, right? And that's because of the Floquet theorem, which says a differential equation with a periodic coefficient. The exact solutions are written that way. That's how you get to block solutions and all of that for periodic potentials. However, there's no derivative in phi in this equation. Phi is simply a parameter. It's not an independent variable.
Yeah, but if you look at E exponent I and phi, this is eigenfunction of rotor. F equals 0.
It's an eigenfunction of LZ. It's an eigenfunction of lots of things.
Expansion and
If phi is actually an independent variable, it's not. It's a parameter of the laser field.
phi is a time-dependent coefficient. It's expansion.
No, it's not.
Okay.
No, it's actually not. Phi is a parameter. That's determined by the laser field, which is input to our Hamiltonian.
It's time-dependent only coefficient. Yeah. Okay.
So, just to give you an idea how this works for the asymmetry, since the questions were asked. The asymmetry is defined as things going right minus things going left. Okay? So all I have to do is take the previous expression, integrate over the right hemisphere and the left hemisphere, but I can do that analytically once I write a few more things in there. But we know we're in the dipole approximation, and so we know that each photon absorbed must change parity, right? And so in this expression, we can write all of that out, simplify it to this, and you'll see the same two amplitudes, except one of them has odd parity, one of them has even parity. So what does that say? It says, to get spatial asymmetry, I have to superpose odd parity states and even parity states. But that's exactly what you expected to find, right? We just showed that comes out of the analysis. Because to get a spatial asymmetry, clearly you need to superpose those things. Okay? But what it also says is because this is even parity, this n is even. This is odd parity, n prime is odd, and so the lowest contribution there, and I'll get down to that. Let's see. Let me do this in order. So for there to be interference to have the CE phase dependence, this amplitude and that amplitude have to overlap in energy. So if I take a typical spectrum, photoelectron spectrum like this, then the 3 photon peak, say, looks like this. Here's my ground state. I absorb 1, 2, 3 photons. This is an odd parity state, and this is what the energy distribution might look like. 4 photons looks like that, 5, and so on. At a lowest order perturbation theory kind of picture. To get CE phase effects, these have to interfere, and of course, the CE phase effects right now are going to be occurring right there. right? Because that's the only place that these different ones overlap, and I need n and n prime to be different. They need different parities, okay? So obviously what I need is for these peaks to get broader, okay? How do I do that? I make a short pulse, because that makes the bandwidth larger. And so now 3 and 4 photons overlap in a much larger area in that shaded, which you can maybe barely see, in the shaded spots there. So you expect CE phase effects to happen there because that's where interference is possible. Okay? And that tells us that the CE phase effects in the asymmetry must have periods, must have frequencies in phi of, actually, let me do it up here. It's going to have cosine phi, sine phi, cosine 3 phi, sine phi, that sort of thing. Only odd frequencies. And so, but that's a completely general statement that applies to any system. And so what I've done here, and I'm not going to obviously tell you about every one of those, but this is a collection basically of all of the results so far, experimental results on asymmetries. Okay? And I will tell you, I can show you in detail offline if you want, that in fact, all of these asymmetries are exactly what we predicted. It's cosine phi, sine phi. Okay? And notice that the systems range from an atom, xenon, to a molecule, D2, to CO, a more complex one, BCl, a more complex molecule, argon, nitrogen, and even over here, silicon dioxide nanoparticles. Okay? That's not a silicon dioxide molecule, it's an actual nanoparticle. And in fact, you see the same periodicity because our approach is completely general. So one way to treat complex systems is to find these general properties. Okay? I'll just say that we can do the same thing for the yields. Because in some sense, if you want to control chemical reactions, you don't want to control the direction of the fragments. You want to control the yields of the different chemically distinguishable species. Okay? And the punchline there is that we can do the same thing, except now that it states with the same parity have to overlap, which means if you want to control them with CE phase, you're down there. Okay? The periods, the frequencies you should see are 1, 2, 4, and so on. So again, all the results so far, experimentally, and we see the correct periodicity from atoms to molecules to complicated molecules, acetylene and ethylene and whatever the one with 6 is. Okay? So just to sum up, we've been able to treat these complex systems with this control parameter in a completely analytic way. Okay? It works for all the systems we've seen so far. And it generalizes. We can do the same thing essentially for any periodic field parameter. So the 2-color delay phase, the polarization of the field, all of these things can be treated the same way. So we can have analytic expressions so we can derive general properties. Okay? Any case, the other thing that we can do is use this formulation to go backwards. So with the formulation, if we have the experimental observable, we can in fact do the Fourier transform of the observable to extract information about the photon pathways. Okay? And in strong fields, there's really no other way to do this. Okay? And with that, I will stop. Thanks.
We have a brief time for some questions.
So now you talk mostly about like the properties of the particles that you ionize.
Yes.
So can you use this idea also to say something about the photons? Harmonic spectrum?
Oh, for harmonic generation, for instance? Yeah. Because, I mean, fundamentally, the harmonic generation is a property of the wave function. And so we can write the wave function down so we can write. Yeah. And in fact, I actually have it just to make the point. There's the theory. Oh, whoops. I didn't write the theory down. Okay, anyway. We can do it for higher harmonic generation. Yeah. Yeah. So we can explain the CE phase dependence of high harmonic generation as well.
One more question.
I just wondered that the phi, if you consider the propagation media, whether that phi would change from that so well-defined single parameter.
Propagation in what media? The light pulse in
Yeah.
in what medium?
Just the gas, So
Okay, but these are gas phase experiments done at low densities so that there is no propagation effect on the laser. And in fact, mostly the laser propagates in near vacuum until a narrowly defined target region. So there's nothing, there is no propagation in the medium.
But before and after the focal point, the phi changes by pi over 2.
There's a GUI phase. And so most of these experiments are done with the target overlap before the focal region. So that otherwise you have to average, you're averaging over the GUI phase and you lose CE phase effects.
So this calculation, I understand that you make this expansion in
In the phase, yeah.
Can you independently calculate phi n, or you have to solve the wave function first, then do this expansion equation?
So the way that we actually do this, okay, so here's maybe a few more details. So that's the same equation I showed. Here's the expansion. If you substitute all of that in, this is the new equation you would get for these amplitudes.
Okay, so you have to, I understand.
So hold on.
You have to solve them
No,
simultaneously.
no, hold on. You can solve this, but that's a very difficult problem to solve because you basically just now multiplied your difficulty. However, you can solve this equation for several different phis, do the Fourier transform of it, and reconstruct the whole thing. And basically, Jack, are you listening?
Yep.
That makes it trivially parallel. So you can do all those CE phases in parallel.
So my question is, in this calculation, the field, the classical field is a coherent state, yes?
Yeah.
So that means in the final measurement, they are collapsing into individual n. Yeah, a coherent state is a superposition of the Fock state.
You could say that, yeah.
So that means you can really use the data because it's independent runs
To learn about the field.
to learn about the field, which is entangled with your system.
That's right.
Because after the measurement, you
Yeah,
collapse
yeah.
it.
And there is a paper actually talking about this, that these sort of CE phase measurements are a way to get at the state of the field.
Oh, that's good. Yeah, because it should be
Yeah,
straightforward.
yeah. I wouldn't mind some of your quantum optics guys. I might pick your brains about whether you believe this paper or not, though.
I think actually, I'm gonna have to move on.
Yeah.
Save any discussion for lunch. Let's thank Brett one more time.